What if everything you know about time, the steady tick of seconds, the unshakable arrow of history, is just a fleeting chapter in a story much older than existence itself? Picture a realm where the word before loses all meaning, where the very idea of sequence dissolves into something stranger, more primordial. This isn't science fiction. It's the frontier of cosmology, where scientists grapple with the enigma of the time before time, a phase so alien that even our most advanced physics strains to describe it. Think of it like standing at the edge of an endless ocean, trying to imagine what lies beneath the surface, except this ocean is the birthplace of reality, and its depths hold the secrets of how dimensions themselves came to be. We're about to embark on a journey into one of the most profound mysteries of the cosmos, the multiphase birth of dimensional space. Imagine the universe as a tapestry, woven not just in space, but in layers of time and dimensionality we can scarcely perceive. Some theories suggest our reality might be just one thread in that tapestry, emerging from a cascade of quantum fluctuations in a higher dimensional void. Others propose that what we call the Big Bang wasn't a true beginning at all, but a transition, a moment when a previous state of existence folded in on itself, giving rise to the dimensions we recognize today. The questions this raises are as dizzying as they are thrilling. Could there have been a proto-time before time, a space before space? This is where the boundaries of human understanding blur into the realm of the extraordinary. Over the next while, we'll explore cutting-edge ideas that challenge our most fundamental assumptions, from quantum foam bubbling at the roots of reality to the mind-bending possibility that our universe is just one iteration in an endless cycle of creation and dissolution. Along the way, we'll confront theories that sound like they're pulled from the pages of a metaphysical epic, yet are grounded in the rigorous work of physicists daring to peer beyond the veil of the observable. So suspend what you think you know about beginnings and endings. What lies ahead isn't just a story about how the universe came to be, it's a glimpse into the very mechanisms that might govern all existence, past, present, and beyond. To grasp the concept of timelessness, we must first let go of everything familiar. Imagine a state where the word when has no meaning, no past to point to, no future to anticipate, not even a present moment to anchor yourself. This isn't just an absence of time, it's a realm where time as we know it cannot exist. Ancient creation myths often described this as a formless void, a boundless nothingness that predated the gods themselves. The Hindu Rigveda speaks of a darkness swallowed by darkness, while the ancient Greeks imagined chaos, a yawning abyss where order had yet to take shape. These aren't just poetic metaphors, they're humanity's earliest attempts to describe the indescribable, a phase where reality hadn't yet begun to unfold. Modern physics approaches this mystery from a different angle. Theories like loop quantum gravity suggest that before the Big Bang, space-time might have been a seething quantum foam, a turbulent sea of potential where dimensions flickered in and out of existence. In this state, cause and effect wouldn't follow the rules we're used to. Events wouldn't happen in sequence, they'd overlap, reverse, or simply cancel each other out. It's like trying to trace the path of a single raindrop in a hurricane. Even the concept of before becomes slippery. Some models propose that our universe emerged from a collision of higher dimensional membranes, while others argue time itself could be cyclical, with each Big Bang not a true beginning but a reset, a cosmic breath in an endless cycle of expansion and collapse. What makes this so mind-bending is that our tools for understanding reality, mathematics, observation, even logic, are built on the assumption that time flows in one direction. But in a timeless state, those tools might be useless. Think of it like trying to navigate a pitch-black room with a compass that only works in daylight. This is why some physicists turn to metaphysics, borrowing ideas from philosophy to bridge the gap. The philosopher Immanuel Kant argued that time isn't a feature of the universe itself, but a framework our minds impose to make sense of it. If he was right, then timelessness isn't just a physical state. It's a glimpse behind the curtain of human perception. Yet for all the uncertainty, one thing is clear. The idea of timelessness forces us to confront the limits of our imagination. Whether through myth or equations, we're reaching for something beyond the edges of comprehension, a shadowy realm that might hold the keys to existence itself. And that's what makes this quest so exhilarating. Every theory, every failed experiment, every moment of confusion brings us closer to truths that could rewrite not just the story of our universe, but the very nature of reality. Even the emptiest void we can observe isn't truly empty. Peer closely enough, and space itself crackles with energy particles appearing and vanishing in flashes so brief they defy measurement. These quantum fluctuations aren't just curious quirks of physics. They could be cosmic echoes, faint tremors left over from an era before our universe began. Think of them like ripples on the surface of a pond after a stone has sunk, hints of a deeper disturbance lost to time. This is where the boundary between science and speculation starts to blur. Loop quantum gravity, one of the boldest frameworks challenging classical physics, paints a picture of space-time as a granular fabric. At unimaginably tiny scales, this fabric dissolves into a seething foam where dimensions tangle and untangle. In this realm, the Big Bang might not have been a singular explosion but a rebound, a moment when a previous universe collapsed inward, only to surge outward again in a new configuration. It's as if reality itself breathes, expanding and contracting in cycles spanning trillions of years. String theory takes this even further. Imagine our universe as a three-dimensional shadow cast by vibrating strings in a higher dimensional space. In this view, the Big Bang could have been triggered by a collision between these cosmic membranes or brains, releasing energy that crystallized into the dimensions we inhabit. What's startling is that these theories don't just add to our timeline, they erase the idea of a definitive beginning altogether. Time becomes a loop, a Möbius strip with no true start or end. But how do we test ideas that reach beyond the observable universe? Some physicists look for fingerprints in the cosmic microwave background, the afterglow of the Big Bang, searching for anomalies that might reveal collisions with other universes. Others simulate quantum conditions in labs, recreating microscopic glimpses of spacetime's primordial chaos. The challenge is immense. It's like trying to reconstruct a forest from a single leaf, or deciphering an entire symphony from a single note. Yet, even without definitive proof, these theories transform how we see our place in the cosmos. If the universe cycles through endless births and deaths, then stars, galaxies, even life itself may have risen and fallen countless times before. The atoms in your body could have once been part of a forgotten cosmos, scattered across eons only to reassemble here now as you. This isn't just about origins, it's about connection. A reminder that existence might be far stranger, far grander, and far more mysterious than we ever dared to dream. What if the solid, three-dimensional world around you, the chair you're sitting on, the screen in front of you, even your own hands, is nothing more than an elaborate illusion? A shadow cast by something far stranger happening at the edge of reality itself. This isn't the plot of a sci-fi movie. It's the heart of the holographic principle, one of the most radical ideas in modern physics. Imagine the universe as a cosmic cinema where the film we're watching, our reality, is actually being projected from a two-dimensional surface we can't see. Every event, every particle, even the passage of time might just be data encoded on a distant boundary, like pixels on a screen. The roots of this mind-bending concept trace back to an unexpected place: black holes. In the 1970s, physicist Jacob Bekenstein discovered something astonishing. The amount of information a black hole can hold isn't proportional to its volume, but to its surface area. It's as if the entire contents of a three-dimensional space could be painted onto its two-dimensional boundary. Later, string theorists like Leonard Susskind and Gerard T. Hooft took this further, proposing that this might not just apply to black holes, but to the entire universe. Think of it like a hologram on a credit card. Tilt it and you see depth, texture, even motion, but at its core, it's just a flat, patterned surface. If the holographic principle holds, it would mean that space as we experience it isn't fundamental. The three dimensions we move through could emerge from interactions on a distant, two-dimensional plane, like waves rising from the ocean's surface. This challenges our most basic assumptions about reality. We think of space as something tangible, something there, but what if it's more like a performance, a dynamic projection from a deeper, hidden layer? Even time might not be what it seems. In this framework, the past, present, and future could be like frames in a movie, already encoded on that cosmic boundary, waiting to unfold. Critics argue that the holographic principle remains speculative, lacking direct experimental proof. But intriguing clues are emerging. Some versions of string theory suggest that the mathematics describing a higher dimensional universe can be perfectly mirrored by equations operating in fewer dimensions, a kind of cosmic duality. Meanwhile, experiments with quantum entanglement reveal strange, instantaneous connections between particles that seem to ignore space and distance, as if they're linked through some deeper, hidden structure. The implications are staggering. If our reality is a hologram, then free will, the flow of time, even the boundaries between objects might be secondary phenomena, illusions woven into the fabric of perception. It raises questions that border on philosophy. What does it mean to exist in a universe where the stage itself is an illusion? Whether the holographic principle is ultimately proven or not, it forces us to confront the limits of human intuition. We're like flatlanders trying to grasp the third dimension, unaware that the truths we cling to might be fragments of a far grander, far stranger picture. And that's the real power of these ideas, not just to rewrite textbooks, but to expand the very horizons of what we think is possible. The world around us seems so solid, so tangible, three dimensions of space, one of time, all neatly woven into the fabric of everyday experience. But what if this is just the surface layer of a far richer reality? String theory, one of the most ambitious frameworks in modern physics, suggests that the universe might be humming with hidden dimensions, 6 or 7 more, curled so tightly at the subatomic level that even our most powerful microscopes can't detect them. Picture a garden hose stretched across a field. From a distance, it looks like a simple line, one dimension, but up close, you realize it's actually a cylinder with a circular dimension wrapped around its length. Now imagine that same principle applied to the fabric of spacetime itself, with tiny, coiled dimensions woven into every point in our familiar four-dimensional world. These extra dimensions aren't just mathematical curiosities. They could be the missing link in one of physics' greatest puzzles, the unification of gravity and quantum mechanics. For decades, these two pillars of modern science have refused to harmonize. Gravity shapes the cosmos on grand scales, bending galaxies and sculpting the universe, while quantum mechanics governs the chaotic dance of particles at the smallest scales. Yet when physicists try to merge them, the equations break down into infinities. String theory proposes a breathtaking solution. What if gravity isn't weaker than the other forces, but simply diluted, its strength seeping into these hidden dimensions. It's like comparing the roar of a concert in a stadium to the muffled sound you'd hear from outside the walls. The music isn't quieter, it's just spreading into spaces you can't see. But how could these dimensions have shaped the universe's birth? Some models suggest that in the earliest moments of existence, all dimensions, both the familiar and the hidden, were compact and symmetrical. Then, as the cosmos expanded, three spatial dimensions stretched outward, while the others remained tightly wound, like scrolls locked in a cosmic vault. This unfurling might have imprinted itself on the laws of physics, determining everything from the strength of gravity to the behavior of particles. Imagine blowing up a balloon with intricate patterns drawn on its surface. As it expands, some designs stretch into clarity, while others shrink into obscurity. In the same way, the geometry of these hidden dimensions could dictate why matter behaves as it does, why certain constants in nature have the precise values they do, even why our universe is stable enough for life to arise. The implications don't stop there. If these dimensions exist, they might host phenomena unlike anything in our observable universe. Particles could oscillate through them, appearing to vanish and reappear in our dimensions like ghosts passing through walls. Some theories even suggest that other universes with their own laws of physics could be mere millimeters away from us, separated only by the folds of these higher dimensional spaces. It's as if we're living on one page of a vast, multidimensional book, unaware of the stories written on the pages above and below us. Yet for all its elegance, string theory remains controversial. Without experimental proof, it's often criticized as a beautiful idea trapped in the realm of speculation. But scientists aren't giving up. Some search for subtle gravitational anomalies, tiny deviations from Newton's laws at microscopic distances, that could betray the presence of extra dimensions. Others hunt for signatures in particle colliders, hoping to catch a glimpse of higher dimensional resonances or even miniature black holes that would wink into existence if these dimensions are real. It's a bit like listening for echoes in a dark cave, straining to hear the faintest whisper of something vast and unseen. What's striking is how these ideas force us to confront the limits of human perception. We evolved to navigate a world of three dimensions, to intuit cause and effect, to trust our senses. But the universe, it seems, operates on rules that defy intuition. Whether string theory's hidden dimensions are confirmed or not, they remind us that reality is far stranger, far more intricate than our everyday experience suggests. And that's the true gift of this exploration, not just answers, but better questions, and a humbling sense of wonder at the mysteries still waiting to be uncovered. Dark energy is the cosmic wildcard, an invisible force pushing the universe apart faster than gravity can pull it together. But what if this mysterious pressure isn't just some exotic ingredient in the cosmos? What if it's a whisper from the very birth of dimensionality itself? Picture a balloon inflating unevenly, its surface stretching thinner in some places, thicker in others. Now imagine that balloon is space-time, and those variations in tension are echoes of dimensions unfurling in ways we can't directly see. This isn't pure speculation. Some of the boldest theories in physics suggest dark energy might be the fingerprint of higher dimensional physics leaking into our observable universe. The math gets dizzying here, but the core idea is startlingly elegant. If extra dimensions exist curled up like microscopic scrolls at every point in space, their geometry could be evolving even now. As these hidden dimensions stretch or compress, they might release energy into our familiar three-dimensional realm, subtly tweaking the expansion rate of the cosmos. It's a bit like feeling a breeze through a cracked window without ever seeing the storm outside. The cosmic microwave background, that ancient afterglow of the Big Bang, shows faint temperature variations that some researchers interpret as scars from this dimensional unfolding. Think of it as cosmic origami, the creases left behind as reality folded itself into the shape we recognize today. String theory offers a provocative twist. In certain models, dark energy arises when higher dimensional branes, those theoretical membranes floating in a bulk space, gradually drift apart. The energy of their separation could manifest in our universe as the repulsive force we call dark energy. It's as if the space between two pages in a book were slowly increasing, and that tension made the words on our page stretch farther apart. Even loop quantum gravity, string theory's rival, hints at connections between dark energy and primordial dimensional fluctuations. In this view, the acceleration of the universe might not be a recent phenomenon, but a relic of spacetime's quantum-grained structure snapping into place during its earliest phases. The implications are profound. If dark energy is tied to dimensional unfolding, it could mean the universe's expansion isn't just a one-way trip toward cold, empty darkness. Instead, we might be witnessing an ongoing transformation, a continuation of the same process that birthed dimensions in the first place. Some models even suggest that dark energy could fluctuate over cosmic timescales, its strength waxing and waning as hidden dimensions reach new equilibriums. Imagine a pendulum swinging in a pitch-black room. We can't see the pendulum, but we feel the breeze as it passes. Dark energy might be that breeze, hinting at motions in the unseen architecture of reality. Of course, not all physicists are convinced. Skeptics argue that linking dark energy to extra dimensions is like using a riddle to solve a mystery. It replaces one enigma with another. Alternative explanations like vacuum energy or modifications to Einstein's gravity remain in play, but here's what's fascinating. Even if these theories are wrong, they're usefully wrong. They force us to ask deeper questions. Why does dark energy have the precise value it does? Why now? The fact that its effects became dominant roughly 5 billion years ago, coinciding with the rise of complex structures in the universe, might not be an accident. Could there be a feedback loop between dimensional evolution and the complexity of matter? Experiments are already probing these ideas. The Euclid Space Telescope, launched in 2023, maps dark energy's distribution with unprecedented precision, searching for patterns that might betray higher dimensional influences. Meanwhile, tabletop experiments with ultra-cold atoms test whether gravity behaves differently at microscopic scales, a potential smoking gun for hidden dimensions. It's a bit like detectives reconstructing a crime scene from scattered clues, except the scene is the entire history of space-time, and the clues are written in geometry itself. What's striking is how these ideas reframe our place in the cosmos. We're not just passengers on an expanding raft of space. We're witnesses to a process that might span dimensions beyond our perception. Dark energy could be the universe's way of remembering its origins, a cosmic habit, like a tree's roots still shaped by the contours of the seed it once was. And that's the real magic here. These theories don't just fill gaps in our knowledge. They weave the universe into a richer, stranger tapestry, where every unanswered question is an invitation to look deeper. The notion that our universe might be just one in an endless chain rising from the ashes of its predecessor, only to collapse and seed the next, isn't just science fiction. It's a thread woven through human thought for millennia. Ancient Hindu texts describe a cosmic rhythm of creation and destruction, where universes emerge and dissolve like bubbles in an eternal ocean. The Rigveda speaks of cycles lasting billions of years, each presided over by a breath of the god Brahma. Meanwhile, the Mayans envisioned time as a series of nested wheels, each turn birthing a new world. These aren't just myths, their startlingly prescient intuitions about the nature of reality, now finding eerie echoes in the equations of modern physics. Take conformal cyclic cosmology proposed by Nobel laureate Roger Penrose. In this model, the universe doesn't end in heat death or a big crunch, but in a state so stretched and cold that all particles lose their sense of scale. Time and distance become meaningless, a reset button for reality. From this featureless void, a new Big Bang ignites, not from a singularity, but from a transformation. Penrose calls these cycles eons, each one inheriting subtle imprints from the last. It's as if the universe is a phoenix, perpetually reborn from its own ashes, carrying faint scars of its past lives. The beauty of this idea lies in its symmetry. Just as black holes preserve information in their event horizons, conformal cyclic cosmology suggests that the cosmic microwave background, the afterglow of our Big Bang, might contain faint traces of an earlier eon. Penrose and his collaborators claim to have spotted these imprints, concentric rings in the microwave sky where temperatures vary slightly, like ripples from a pebble tossed into a pond long before time began. Critics argue these patterns could be statistical flukes, but if confirmed, they'd be the first tangible evidence of a universe before our own. String theory offers a different take on cyclicality. In some versions, colliding higher dimensional brains trigger big bangs over and over, like cymbals clashing in an endless cosmic symphony. Each collision releases energy that forms a new universe, while the brains rebound and eventually collide again. The cycles might not be identical. Some universes could have more dimensions, different physical constants, even alternate laws of physics. Imagine a library where each book is a universe, and every time you finish one, the next has the same cover but a wildly different story inside. What's fascinating is how these modern theories grapple with the same paradoxes ancient sages did. If time resets with each cycle, can we even speak of a before or after? Hindu philosophy sidestepped this by positing a timeless, unchanging reality behind the cycles, a concept mirrored in Penrose's conformal geometry, where the endpoint of one eon blends seamlessly into the start of the next. It's like a snake swallowing its own tail, a loop with no true beginning or end. Yet cyclical models aren't without challenges. Entropy, the measure of disorder, seems to increase with each cycle, suggesting future universes might grow colder, emptier, more diluted. Could the cycles eventually wind down? Some theorists propose that quantum effects might recharge entropy, like a cosmic battery resetting itself. Others argue that in a multiverse of cycles, only the universes capable of sustaining complexity, like ours, would ever be observed, a twist on the Anthropic Principle. Whether these theories hold or not, they transform how we see our place in the cosmos. If the universe is cyclic, then every atom in your body might have once been part of a trillion ancient stars, 100 forgotten Big Bangs, a chain of existence stretching back further than imagination can reach. The night sky isn't just a static backdrop, it's a single frame in a film playing on loop, a story written in fire and reborn again and again. And that's the real power of these ideas, not just to explain origins, but to connect us to something vast, ancient, and unimaginably alive. Imagine a cosmic froth, an infinite sea of universes bubbling into existence, each with its own unique fingerprint of physical laws, its own recipe of dimensions. This is the multiverse, a concept that stretches the boundaries of reality itself. Some of these universes might have 4 spatial dimensions, others 7 or 10. Some might be flat and static, while others twist like Möbius strips, folding back on themselves in ways that defy our 3-dimensional intuition. The wild diversity isn't random. It's the inevitable outcome of the same quantum chaos that birthed our own cosmos. Inflationary theory, the leading framework for the Big Bang's explosive expansion, suggests that our universe is just one pocket in a vast inflationary landscape. Picture a boiling pot of water. Each bubble rising to the surface is a separate universe, inflating rapidly before cooling into its own distinct structure. The key here is quantum fluctuation, tiny, random variations in energy that, during inflation, get stretched to cosmic scales. These fluctuations don't just create galaxies, they can also determine the very dimensionality of space. In one bubble, 3 dimensions might stabilize while others curl up. In another, 6 dimensions could remain expansive, creating a reality where gravity behaves differently or light travels in ways we can't begin to visualize. Brainworld scenarios take this even further. Imagine our universe as a slice of bread floating in a higher dimensional loaf. Other slices, parallel brains, might hover mere millimeters away in an unseen dimension, each hosting its own cosmos with alien physics. In some versions of string theory, collisions between these brains could trigger big bangs, seeding new universes like sparks from a cosmic grindstone. The terrifying beauty of this idea: we might never detect these neighboring realities directly, because all known forces except gravity are trapped within our own brain. Gravity's whispers could be the only hint of worlds just beyond our reach. Yet the most mind-bending possibility isn't just that other universes exist, it's that their dimensional structure might make them utterly unrecognizable. A universe with 4 spatial dimensions could host geometric objects beyond our comprehension, hyperspheres, tesseracts, knots that untie themselves. Time might flow backward in some, or loop like a broken record. In others, the very concept of distance could be meaningless, with particles entangled across infinite reaches instantaneously. The late physicist Max Tegmark categorized these possibilities into 4 levels of multiverses, from the merely distant to the cosmologically surreal. Level 1, universes like ours, forever hidden beyond the cosmic horizon. Level 4, realities where mathematical structures themselves become alternate physics, a playground of pure abstraction. So how do we test these ideas? Some scientists scour the cosmic microwave background for bruises, anomalies that might hint at a collision with another universe. Others simulate high-dimensional physics in supercomputers, probing how alternate dimensionality would warp the laws we take for granted. And then there's the eerie possibility that black holes are portals, their singularities punching through to other brains or birthing baby universes in their cores. It's speculative, sure, but when the alternatives are infinite diversity or one lonely universe, speculation is the only tool we've got. What's striking isn't just the scale of these ideas, but their humility. If the multiverse is real, then every law of physics we've ever discovered, every constant, every symmetry, might just be a local bylaw, a quirk of our particular bubble. The speed of light, the strength of gravity, even the number of dimensions could be cosmic accidents. It's like growing up in a valley and believing the entire world shares your climate, until one day you crest the mountains and see deserts, oceans, ice caps, realities so foreign they rewrite your understanding of normal. That's the multiverse's gift, not just new worlds, but a new way to see our own. Black holes aren't just cosmic vacuum cleaners. They might be the universe's most twisted architects, bending space-time into shapes so extreme they could tear open doorways to realms beyond our own. Picture a whirlpool in the fabric of reality, where gravity's grip is so overpowering that not even light can escape. But what happens to all that swallowed matter and energy? Some theories suggest they don't just vanish. Instead, they might be squeezed through a cosmic bottleneck, emerging somewhere or someone else entirely. Take the Einstein-Rosen bridge, often called a wormhole. At the heart of certain black holes, mathematical models show space-time curving into a tunnel, potentially linking distant regions of our universe or even different universes altogether. It's like folding a piece of paper so 2 points touch, except the paper is reality itself, and the pencil poking through is matter being shuttled across dimensions. The catch: these wormholes are notoriously unstable, snapping shut faster than a blink unless some exotic force like negative energy props them open. But in the quantum foam of spacetime, where tiny wormholes might flicker in and out of existence, who's to say nature hasn't found a way? Even wilder is the idea that black holes could be cosmic recycling plants. In loop quantum gravity, a black hole's collapse doesn't end in a singularity, a point of infinite density, but rebounds in a quantum bounce, the result. A white hole spewing out everything the black hole devoured, potentially into a newborn universe with its own spacetime structure. Imagine a tree growing from a seed, except the seed is a dying star's remains, and the tree is an entire cosmos branching off in some higher dimensional garden. This isn't just poetic imagery. Equations suggest these baby universes could inherit subtle traits from their parent, like a cosmic DNA that shapes their laws of physics. Then there's the holographic twist. If our universe is a projection from a two-dimensional boundary, as some theories propose, then black holes might be glitches in that cosmic code, places where information gets scrambled but never truly lost. Like a file compressed to the brink of deletion, only to be reconstructed in another format. This could explain the infamous black hole information paradox, where quantum mechanics insists information can't vanish, even as black holes seemingly erase it. The answer: that data might be encoded on the event horizon's surface, a frozen hologram waiting to be decoded in whatever reality lies beyond. Of course, skeptics abound. Wormholes and white holes remain hypothetical, and no one's observed a universe budding off a black hole yet. But consider this: the cosmic microwave background shows faint, circular anomalies that some researchers, like Roger Penrose, argue could be scars from ancient black hole collisions in a prior universe. If true, our cosmos might already bear fingerprints from dimensions long gone. Meanwhile, labs are simulating black hole conditions using ultra-cold atoms and lasers, watching how information behaves at the edge of annihilation. It's like trying to reconstruct a fire from its smoke, difficult but not impossible. What's mesmerizing isn't just the science but the philosophy. If black holes can bridge worlds or birth new ones, then destruction and creation might be two sides of the same coin. Every star swallowed, every galaxy devoured, could be sowing seeds for realities we'll never see. It's a humbling thought that the darkest objects in the universe might also be the most luminous with possibility. The universe's opening act defies all expectations. Why would an unfathomably hot, dense singularity, a state of maximum chaos, suddenly unfurl into the exquisitely ordered cosmos we see today? This is the enigma of initial conditions, a puzzle that keeps physicists awake at night. Normally, systems evolve from order to disorder, like an ice cube melting in the sun. But our universe did the opposite, starting in a state of bizarrely low entropy, as if a shattered teacup spontaneously reassembled itself. The odds of this happening by chance are astronomically small, so what stacked the deck in reality's favor? One daring idea is quantum tunneling from absolute nothingness. Imagine a void so complete it lacks not just matter, but space and time themselves. In this abyss, quantum fluctuations could trigger a spontaneous leap, a cosmic roll of the dice where nothing briefly borrows energy to become something. It's like a bubble forming in an infinite void, except the bubble contains an entire universe. Theoretical physicist Alexander Vilenkin visualized this as a quantum nucleation event, where our cosmos emerges like a droplet condensing from vapor. The math suggests that once this bubble appears, inflation takes over, stretching it exponentially into the universe we recognize. But here's the catch. This process still doesn't explain why the initial entropy was so improbably low. That's where meta-time enters the conversation. Some models propose that our Big Bang wasn't a true beginning, but a phase transition within a timeless, higher dimensional arena. Picture a frozen lake cracking under its own weight. The ice isn't deciding where fractures will form, but its structure dictates the pattern. Similarly, if the underlying architecture of reality prior to our universe had certain symmetries or constraints, it might have funneled the Big Bang into that peculiar low-entropy state by necessity. Physicist Sean Carroll compares this to how water molecules, when cooled, naturally crystallize into ice's orderly lattice. The system chooses order not by chance, but because deeper laws demand it. Another provocative angle comes from loop quantum cosmology, which suggests the Big Bang might have been a rebound. In this view, a previous universe collapsed not into a singularity, but into an ultra-dense state where quantum gravity effects caused a cosmic bounce. The outgoing phase inherited a low-entropy configuration from the geometry of the collapse, like a spring compressed to its limit and then released with perfect symmetry. This wouldn't just explain the initial conditions, it would weave our universe into an endless tapestry of cycles, each birth echoing the one before. Yet perhaps the most radical solution is that there is no problem at all. The Anthropic Principle argues that we observe this improbable state simply because it's the only one that allows life to exist. In a hypothetical multiverse where countless universes spawn with random initial conditions, only those rare, finely tuned versions that achieve low entropy could ever host galaxies, planets, and minds capable of pondering the mystery. It's like walking into a room and finding a deck of cards stacked in perfect order, not because someone arranged it, but because you couldn't have walked into any of the rooms where the cards were scattered. The search for answers is far from over. Some theorists are exploring holographic principles where the universe's initial conditions are encoded on its boundary, like a cosmic barcode. Others speculate that time itself might be emergent, crystallizing from a more fundamental network of relationships, which would mean the start of the universe wasn't an event in time, but the moment time came into being. Each hypothesis peels back another layer of the mystery, revealing not just how our story began, but how profoundly strange the script of reality might truly be. Time crystals sound like something ripped from a science fiction novel, structures that pulse and oscillate without ever absorbing energy, like a clock that ticks forever without being wound. But these aren't fantasy. They're real, experimentally verified phases of matter that defy one of the universe's most fundamental rules, time's arrow. Normally, physical systems settle into equilibrium, like a cup of coffee cooling to room temperature or a pendulum slowing to a stop. Time crystals break this mold. They're locked in perpetual motion, repeating their patterns not because of external forces, but because of the quantum scaffolding of reality itself. The key to their strangeness lies in symmetry breaking. Think of a frozen lake. Liquid water looks the same no matter how you rotate it. It has perfect symmetry. But when it freezes into ice, that symmetry shatters. The molecules align in a specific pattern, choosing one orientation over countless others. Time crystals do something similar, but with time instead of space. In a universe where the laws of physics are usually indifferent to time's direction, a movie played forward or backward, these crystals pick a rhythm, a preferred tick-tock that repeats indefinitely. It's as if nature, for just this one case, whispers that time has a grain, a hidden texture we're only beginning to sense. What's truly startling is how time crystals might connect to the universe's earliest moments. Some theorists speculate they're relics of a pre-temporal phase, quantum echoes from an era when time as we know it hadn't yet crystallized. Imagine a world without clocks, where cause and effect aren't yet chained to sequence, a state where time crystals could have formed as transient structures, like ice flows on a primordial sea. If true, studying them might offer clues about how time itself emerged from timelessness. The implications ripple outward. If matter can exist in phases that ignore energy decay, what does that say about the nature of conservation laws? Could there be other, even weirder states waiting to be discovered? Experiments with trapped ions and superconducting qubits have already shown time crystals in the lab, but their potential stretches far beyond tabletop curiosities. Some models suggest they could be the building blocks of fault-tolerant quantum computers, their stable rhythms protecting information from the chaos of decoherence. Others wonder if they might exist naturally in extreme environments, neutron stars, black hole horizons, or even the fabric of spacetime itself. Yet the deepest mystery isn't how time crystals work, but why they're allowed to exist at all. They seem to dance on the edge of physics rulebook, hinting at a larger, stranger playbook we haven't yet uncovered. Every oscillation is a question. What else is possible in a universe where time itself can freeze into patterns? The answers might rewrite not just our understanding of matter, but of reality's most fundamental rhythms. What if the Big Bang wasn't a bang at all, but a crash? A cosmic fender bender in a reality far stranger than our own. That's the heart of the Echpirotic universe model, a radical rethink of cosmic origins inspired by string theory's most audacious ideas. Picture two vast, floating sheets, higher dimensional membranes or brains drifting through an unseen expanse. These aren't just abstract concepts. In this framework, they could be entire universes, each with their own physics, their own dimensions, their own history. And when they collide, the energy of that impact might not just shake the foundations of reality, it could birth an entirely new cosmos. The Echpirotic scenario flips traditional cosmology on its head. Instead of a singularity exploding outward from infinite density, this model proposes that our universe began when two brains smashed together like cymbals in a dark symphony. The heat and turbulence of that collision would mimic the conditions we attribute to the Big Bang, but with a crucial difference: no singularity, no nothingness, no paradox of infinite density. It's as if the universe didn't emerge from a point, but from a plane, an unfathomably vast surface shuddering with the aftershocks of impact. String theorists Neil Turok and Paul Steinhardt, key architects of this idea, saw it as a way to sidestep inflation's lingering puzzles. Inflation, the leading theory for the universe's exponential early expansion, does a brilliant job explaining why the cosmos looks so uniform on large scales. But it relies on a mysterious inflattened field, a cosmic accelerator with no direct evidence. The Echpirotic model, by contrast, suggests that the smoothness of our universe comes from the brains themselves. Imagine two sheets of paper pressed together. As they near collision, quantum fluctuations stretching across their surfaces would imprint themselves as the seeds of galaxies, neatly explaining the large-scale structure we observe without needing inflation's magic. But here's where it gets wild. If our universe is the aftermath of a brain collision, what happened to the brains themselves? Some versions of the theory suggest they recoiled after impact, bouncing apart like springs, only to be drawn together again by higher dimensional gravity. This sets up a cyclic universe, one where cosmic history repeats in endless cycles of collision, expansion, and rebirth. Each Big Bang becomes less of a beginning and more of a reset, a turn in an infinite cosmic dance. Critics, though, aren't sold. For one, the Echpirotic model struggles to explain the universe's startlingly low entropy at the Big Bang, the same puzzle that haunts other theories. If the pre-collision brains were in a high entropy state, why would their collision produce something so orderly? Others point to the lack of direct evidence for higher dimensions or floating brains. Without experimental confirmation, the theory remains a beautiful but speculative sketch. Yet the Echpirotic universe refuses to fade into obscurity. Some researchers argue that gravitational wave astronomy might one day uncover traces of brain collisions in the cosmic microwave background, subtle swirls or scars left by the violence of our origins. Others explore how colliding brains could produce not just our universe, but a multiverse, with each impact birthing a new cosmos with its own unique physics. What's undeniable is how this idea stretches our imagination. The notion that existence could spring from a collision of unseen realities forces us to confront how little we truly grasp about the canvas of the cosmos. Whether the Echpirotic model stands or falls, it reminds us that the universe's origin story might be stranger, richer, and more interconnected than we ever dared to dream. The universe has a stubborn habit of moving forward. Eggs shatter but never reassemble, coffee cools but never spontaneously reheats. This relentless march is the arrow of time, and its engine is entropy, the tendency of systems to slide from order into disorder. But here's the cosmic head-scratcher. If disorder always increases, why did our universe start with entropy so inexplicably low? It's as if someone shuffled a deck of cards and it landed in perfect numerical sequence, a statistical miracle begging for an explanation. Some physicists argue this isn't just luck. The secret might lie in how dimensions themselves unfolded during the universe's birth. Picture a newborn cosmos where all dimensions visible and hidden are compact and symmetrical, like a tightly wound spring. As inflation kicks in, 3 spatial dimensions stretch outward while others curl up at microscopic scales. This unfurling could have acted like a cosmic filter, sieving out chaos and leaving behind a pocket of startling order. Think of it like shaking a box of mixed puzzle pieces until one corner accidentally snaps into place. The low entropy starting point wasn't random. It was a side effect of dimensional geometry locking into its stable configuration. But there's a twist. String theory suggests that higher dimensional spaces might have different entropy rules entirely. In a 10-dimensional universe, black holes, the ultimate entropy factories, could behave differently, their event horizons shaped by dimensions we can't perceive. If our 3-dimensional reality is a shadow of this richer structure, then our arrow of time might be a projection of deeper, hidden dynamics. It's like watching a shadow puppet show and assuming the shadows move on their own, unaware of the hands manipulating them from a higher dimension. The stakes here aren't just academic. Without this entropy imbalance, stars wouldn't shine, chemical reactions wouldn't occur, and life itself would be impossible. We're the beneficiaries of a cosmic fluke, or perhaps a necessity. Some theorists, like Sean Carroll, propose that in a multiverse, only universes with low initial entropy can spawn complexity, making our existence a form of observational bias. Others, like Roger Penrose, see the fine-tuning as evidence of something deeper, cycles of universes where each Big Bang inherits order from the geometry of its predecessor's collapse. What's mesmerizing is how this all ties back to time's origin. If dimensions emerged from a timeless quantum foam, their stabilization might have effectively wound up the universe's clock, setting entropy's pendulum in motion. We're not just tracing the history of matter and energy, but the very architecture that made time's arrow possible. And that's the ultimate irony. To understand why time flows forward, we might need to peer back into the timeless void that birthed it. What if the dimensions we move through, the up and down, left and right, even the steady tick of time, aren't fundamental features of reality, but clever illusions? Layers of code in a cosmic simulation so vast, so intricate, that its inner workings are indistinguishable from physics itself. The simulation hypothesis, once relegated to late-night dorm room debates, has gained startling traction among physicists and philosophers alike. At its core is a provocative question: could the multiphase birth of dimensions we've been exploring actually reflect the choices of a programmer crafting the rules of a virtual universe? Think of it like a video game engine. When developers build an open-world game, they don't simulate every atom. They create shortcuts. Forests might be 2D textures until you get close. Distant stars could be mere points of light with no physical substance. Our universe might operate on similar principles. The three spatial dimensions we experience could be an optimized interface, masking a deeper, more abstract reality where space is just data relationships in a higher dimensional processor. Even time might not flow so much as render frame by frame, like a graphics card updating pixels. This isn't just metaphor. Some theorists argue that if our universe is a simulation, its architecture would leave fingerprints, tiny imperfections or optimizations betraying its engineered nature. One clue could be in the very fabric of spacetime. Just as computer code has resolution limits, ever seen a game texture glitch when zoomed in too far? Spacetime might pixelate at the tiniest scales. Experiments hunting for fluctuations in high-energy particle behavior or anomalies in quantum entanglement could reveal these seams in reality's code. Another hint: mathematical constants. If the speed of light or the strength of gravity appear suspiciously tuned to allow complexity, it might not be luck. It could be deliberate calibration. But here's where things get surreal. If dimensions are simulated constructs, their birth might not have been a physical event at all, but an algorithmic initialization, a boot-up sequence where the simulation's parameters were set. The Big Bang could resemble a program launching, its variables defining how many dimensions to render, how time should increment, even how entropy should unfold. This eerily parallels some quantum gravity models where spacetime emerges from more fundamental information networks. It's as if both physics and the simulation hypothesis are circling the same profound idea: that reality's scaffolding might not be material but computational. Not everyone's convinced, of course. Critics argue the simulation hypothesis is unfalsifiable, a slick modern myth with no way to test it. But others counter that even if we can't peek outside the simulation, we might detect its edges from within. Imagine running a program on your laptop that eventually deduces it's inside a computer by spotting processor lag or memory limits. Similarly, if the universe has finite computational resources, there might be measurable energy constraints on complexity or hidden error correction mechanisms woven into physics itself. Some have even proposed that quantum uncertainty, the fuzziness of particles until observed, could be a sign of processing optimization, like a game only rendering objects when players look at them. Whether you find the idea exhilarating or unsettling, it forces a radical shift in perspective. If dimensions are code, then the mysteries we've been unraveling, cosmic inflation, dark energy, even the arrow of time, might not be laws of nature but design choices. And that raises a chillingly beautiful possibility that every breakthrough in physics brings us not just closer to understanding the universe, but to reading the source code of existence itself. Kurt Gerdle, the mathematician who reshaped our understanding of logic, once turned his genius to Einstein's equations of general relativity, and what he found would make even the most seasoned physicist's head spin. His solutions revealed a universe where time doesn't just march forward in a straight line, but can twist into closed loops like a Möbius strip of causality. Picture boarding a spaceship and following a path so meticulously curved that you'd return not just to your starting point in space, but to the very moment you left. You could, in theory, shake hands with your past self, or worse, accidentally prevent your own birth. These aren't just thought experiments. Gerdle's work proved that such time loops, known as closed time-like curves, are mathematically possible in a rotating universe. The implications are staggering. If time can loop, then the universe's birth might not be a one-way street. Some models suggest that in higher dimensional spaces, these loops could knot together like tangled strings, creating regions where the past, present, and future coexist in a single, self-contained braid. Imagine a cosmic loom weaving reality not in a straight line but in interlocking rings, each Big Bang potentially stitched to its own aftermath, or even to other universes entirely. String theorists have toyed with this idea, proposing that higher dimensional brains could warp spacetime so severely that time's arrow folds back on itself, like a snake swallowing its tail. But here's where it gets thorny. Closed time-like curves violate our most intuitive notion of cause and effect. If you could travel back and alter the past, wouldn't that erase the very conditions that allowed you to travel back in the first place? This is the infamous grandfather paradox, and Gerdle's answer was as elegant as it was unsettling. In such a universe, free will might be an illusion. Events on a closed time-like curve would be fixed, unchangeable, more like a record playing on loop than a story you could rewrite. Your attempt to change the past would already be part of the past, woven into the fabric of what always was. Could these loops have played a role in the universe's origins? Some cosmologists speculate that if time behaved this chaotically in the extreme conditions of the early cosmos, it might explain certain fine-tuned features of our reality. Quantum fluctuations, those tiny seeds of galaxies, could have been recycled through time loops, amplifying their effects in a kind of cosmic feedback. Others propose that the universe's low entropy starting point, that inexplicable orderliness at the Big Bang, might be the result of time folding back on itself, like a painter retouching their canvas until the strokes align perfectly. Yet for all their mathematical beauty, Gerdle's universes remain controversial. Observations show our cosmos isn't rotating nearly fast enough to create such time loops, and most physicists assume quantum gravity effects would prevent them from forming. But the deeper lesson lingers. If time can bend into rings under certain conditions, then the linear, irreversible flow we experience might not be fundamental, just a local quirk of our corner of reality. It's a humbling thought that the arrow of time, so central to our lives, could be as malleable as a piece of heated metal, twisting into new shapes in the forges of higher dimensions. And that's the real power of Gerdle's vision, not just to bend time, but to stretch our imagination of what's possible. Symmetry is the silent architect of the cosmos, a principle so fundamental that without it, reality as we know it would dissolve into chaos. Picture the early universe as a featureless sea of perfect balance, where no force stood apart from another, no dimension had yet declared its uniqueness, and even time itself hadn't chosen a direction. This was a realm of pure potential, where the laws of physics hadn't yet fractured into the fragments we recognize today. Then, in a cosmic heartbeat, something extraordinary happened. Symmetry broke. Like a pane of glass shattering into intricate patterns, the universe's flawless symmetry splintered, giving birth to the forces, particles, and dimensions that define our existence. This process, known as symmetry breaking, isn't just a theoretical curiosity, it's the hidden engine behind everything from the magnetism of a fridge door to the vast structures of galaxies. Think of it like a hot, molten metal cooling. As it solidifies, its atoms lock into a crystal lattice, choosing one orientation out of countless possibilities. The universe underwent a similar transformation. In its earliest moments, all four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single, seamless interaction. But as the cosmos expanded and cooled, this primordial symmetry shattered like ice forming on a pond. First, gravity peeled away, then the strong force, and finally electromagnetism and the weak force diverged, each fracture imprinting its signature on the fabric of reality. But here's where it gets even stranger. Symmetry breaking might not have just shaped the forces, it could have literally carved out the dimensions we move through. Some theories suggest that in the universe's fiery infancy, all dimensions were identical, curled and uncurled in perfect harmony. Then, as temperatures dropped, a phase transition occurred. Three dimensions unfurled into the vast expanse we recognize, while the others remained tightly wound, hidden at scales a billion times smaller than an atom. It's as if space-time itself underwent a kind of cosmic origami, folding into the structure we inhabit today. The Higgs field, which gives particles their mass, might be another relic of this process, a kind of quantum frost settling over the universe as it cooled, locking certain symmetries into place while others vanished forever. The echoes of these breaks are everywhere. The very fact that matter outweighs antimatter in our universe could trace back to a symmetry violation in the earliest moments. Even the arrow of time, that relentless forward march, might owe its existence to the one-way crack of symmetry breaking. Like a frozen lake surface splitting under tension, each fracture set the stage for the universe we know, a universe where diversity emerges from unity, where complexity blooms from simplicity. Yet for all its power, symmetry breaking leaves us with haunting questions. Why did three dimensions expand while others stayed hidden? Was this inevitable or the result of some deeper, still unknown law? Some theorists propose that in a multiverse, every possible symmetry break occurs somewhere, with each universe crystallizing into its own unique shape. Others wonder if the breaks themselves are illusions, artifacts of our limited perspective in a higher dimensional reality where symmetry remains unbroken. What's certain is that symmetry breaking isn't just a chapter in cosmology, it's the plot twist that made everything after possible. Without it, the universe would still be a featureless void, a canvas with no brushstrokes. And that's the ultimate irony. The fractures that shattered perfection are the very reason we're here to ponder them. Wormholes might be more than just cosmic shortcuts. They could be time capsules, preserving whispers from the universe's most chaotic beginnings. Picture a tunnel burrowing through an apple, connecting 2 points on its surface. Now imagine that apple is space-time, and the tunnel threads not just through space, but through the very phases of reality's birth. If wormholes exist, their walls might bear scars from when dimensions were still knitting themselves into existence, like tree rings encoding ancient climate shifts. The math behind this is as elegant as it is mind-bending. Einstein's equations allow for wormholes, bridges between distant regions of spacetime, but keeping them stable requires exotic matter with negative energy, a substance that defies everyday intuition. Yet in the quantum foam of the early universe, where energy fluctuations ran wild, such conditions might have been commonplace. Some theories suggest that microscopic wormholes could have formed during the violent transitions between cosmic phases, like bubbles trapped in ice as water freezes. These primordial tunnels wouldn't just link places, they might connect eras, ferrying information from a time before dimensions settled into their current configuration. Here's where it gets stranger. Quantum entanglement, the phenomenon that links particles across vast distances, could be a clue to how wormholes preserve ancient information. Physicists Juan Maldacena and Leonard Susskind proposed that entangled particles might be connected by microscopic wormholes, their seemingly instantaneous communication actually shortcutting through higher dimensional space? If true, then the universe's earliest quantum tangles, forged when dimensionality itself was in flux, might have left echoes in today's entangled systems. It's as if the universe wrote its own history in a code of quantum links, with wormholes serving as the pen. But could we ever detect these relics? Some models predict that if wormholes threaded the universe's birth phases, they'd imprint faint signatures on the cosmic microwave background, subtle temperature swirls or polarization patterns betraying their presence. Others suggest that collapsing wormholes might have spawned primordial black holes, some of which could still lurk in our cosmic neighborhood, their masses revealing clues about the dimensionality of the era they formed in. Imagine a black hole not just as a trapdoor to nowhere, but as a fossil from when spacetime was still learning how to be spacetime, the most tantalizing possibility. Wormholes might offer a backdoor to observing the pre-dimensional void. If a tunnel's throat somehow avoided the violent smoothing of cosmic inflation, its geometry could retain quantum fluctuations from that primordial chaos. Probing one would be like pressing a stethoscope to the universe's cradle, listening for the faint heartbeat of a reality not yet settled into its current form. Of course, this is speculative. Wormholes remain hypothetical, and harvesting data from them would require technologies far beyond our grasp, but the mere possibility reshapes how we see the cosmos. What's clear is that wormholes, if they exist, aren't just shortcuts through space. They're potential archives, threading the needle between the universe's deepest past and its observable present. Every unanswered question about their nature is an invitation to rethink not just how the cosmos is structured, but how it remembers itself. The Boltzmann brain paradox begins with a deceptively simple question. In a universe that lasts forever, how can we be sure we're not just fleeting accidents? Imagine a vast, chaotic cosmos where particles jostle endlessly given enough time. Even the most improbable events become inevitable. Statistically, the random assembly of a fully formed, self-aware mind from the void would be far more likely than the gradual evolution of life over billions of years. These hypothetical consciousnesses, dubbed Boltzmann brains, would blink into existence fully loaded with false memories of a past that never happened, convinced of a reality that isn't there. One moment, nothing; the next, a complete mind hallucinating an entire universe, including the very scientific laws it uses to make sense of itself. This isn't just a quirky thought experiment. It strikes at the heart of cosmology's deepest assumptions. If our universe truly emerged from chaos, why does it appear so ordered? Why trust any observation, even the Big Bang itself? If randomness could fabricate coherent experiences, the paradox forces us to confront the unsettling possibility that our most cherished truths about time's origins might be illusions, artifacts of a brain that assembled itself 5 minutes ago, complete with the illusion of history. Some physicists argue this undermines the entire premise of an infinite, chaotic universe. After all, if Boltzmann brains dominate statistically, why aren't we one of them? Here's where the connection to timelessness gets eerie. In a pre-temporal state, a realm before cause and effect took hold. The distinction between random fluctuation and structured reality might not exist. A Boltzmann brain emerging from such a void wouldn't just question time's flow. It would exist outside time entirely, its fleeting consciousness unmoored from sequence. Think of it like a dream where scenes shift without logic, except the dreamer is the only thing that exists, and the dream includes the false memory of waking up to a universe with rules. This raises a chilling corollary. What if the Big Bang wasn't a true beginning, but a Boltzmann fluctuation on a cosmic scale? A self-contained bubble of order that, like a brain, convinces itself it has a past. Critics counter that the paradox is a reductio ad absurdum, a sign our models of infinity are flawed. Maybe the universe isn't eternal. Maybe mechanisms like cosmic inflation naturally suppress Boltzmann fluctuations, favoring large-scale order. Or perhaps consciousness can't arise from pure randomness. It might require the precise, iterative scaffolding of evolution. Yet the paradox lingers because it exposes a vulnerability in how we infer reality's foundations. If even time's arrow could be a statistical fluke, how do we know anything about the true nature of existence? The most profound takeaway isn't that we might be Boltzmann brains, but that the paradox mirrors the very mystery of time's origin. Both confront us with the same riddle: how does structure emerge from chaos? Whether through quantum tunneling, brains colliding, or cycles of rebirth, every theory of cosmic beginnings is, in some way, an attempt to explain why we're here instead of a fleeting thought in the void. And that's the paradox's gift, not answers, but a reminder that the universe's greatest enigmas are often reflections of our own limitations. Dark matter doesn't just tug at galaxies, it sculpts the cosmos in ways that defy everything we know about physics. Imagine an invisible hand, unseen and unfelt, reaching across billions of light years to weave the universe's grandest structures. We detect its presence through gravity's fingerprints, stars whirling too fast at galaxy edges, light bending around cosmic voids where nothing visible lurks, the very blueprint of the cosmic web traced in shadows. Yet for all its influence, dark matter remains a ghost, a substance that refuses to interact with light, with matter, even with itself. The question isn't just what it is, but where it came from. Could its origins lie beyond the Big Bang, in a realm where dimensions themselves were still taking shape? One provocative idea ties dark matter to the universe's hidden dimensions. If extraspatial dimensions exist curled up tighter than an atom, they might host particles that only occasionally leak into our three-dimensional world. These elusive particles could carry gravitational weight without responding to electromagnetism, making them perfect candidates for dark matter. Picture a room filled with balloons. If you're a two-dimensional being living on the floor, you'd only see the circles where the balloons touch the ground. The rest of their structure, bulging into the third dimension, would be invisible to you. In the same way, dark matter might be the shadow of something far richer, its true nature extending into dimensions we can't perceive. But there's another, even stranger possibility. Dark matter could be a relic of the pre-Big Bang era, a fossil from when time and space were still flickering into existence. Some models of quantum gravity suggest that the universe's birth wasn't a clean break from nothingness, but a phase transition, like water freezing into ice where remnants of a previous state got trapped in the cracks. These remnants, frozen out of equilibrium with the rest of creation, might now drift through galaxies like cosmic afterimages. Think of it like finding prehistoric insects preserved in amber, except the amber is space-time itself, and the insects are particles that remember a time before time. The hunt for dark matter's identity takes physicists to some of the most extreme environments imaginable. Deep underground, detectors filled with liquid xenon wait for a single, telltale collision between a dark matter particle and an atom, an event so rare it's like listening for a whisper in a hurricane. Meanwhile, particle colliders smash matter at energies approaching the Big Bangs, hoping to shake loose clues from extra dimensions or conjure particles that only existed in the universe's first trillionth of a second. Even the cosmos itself acts as a laboratory. When galaxies collide, their dark matter components sometimes separate from visible matter like oil from water, creating ghostly distortions in spacetime that telescopes can map. Yet the most tantalizing hints might come from the dark matter's sheer abundance. There's 5 times more of it than ordinary matter, a ratio that seems suspiciously precise. Some theorists argue this isn't an accident, but a signature of how dark matter was forged. In certain extra-dimensional models, the number of stable dark matter particles is determined by the geometry of those hidden dimensions, like the way a guitar's shape dictates its resonant frequencies. Others propose that dark matter's dominance reflects a cosmic seesaw. For every particle of light matter created in the Big Bang's fury, multiple dark counterparts were left behind, like echoes of a symmetry we don't yet understand. What's clear is that dark matter isn't just a missing puzzle piece, it's a window into realities beyond our perception. Whether it's a higher dimensional refugee, a relic of the pre-Big Bang void, or something even stranger, its discovery wouldn't just solve a mystery. It would rewrite the story of how the universe built itself and perhaps reveal layers of existence we never dreamed were there. Until then, it remains the cosmos's most tantalizing secret, a shadow stretching across space and time, waiting to be deciphered. Black holes don't just consume matter, they devour information itself. Every atom, every photon, every shred of data that crosses the event horizon seems to vanish from our universe, leaving no trace behind. But here's the problem. Quantum mechanics insists information can never truly be destroyed. It might get scrambled, transformed, or hidden, but it can't simply cease to exist. This clash between gravity and quantum theory is the black hole information paradox, and its resolution might rewrite our understanding of reality's deepest layers. One radical solution comes from holography, the idea that our 3-dimensional universe could be a projection from a 2-dimensional surface. Apply this to black holes, and suddenly their event horizons aren't just points of no return, they're cosmic hard drives. As matter falls in, its information gets smeared across the horizon's surface like ink on a page, preserved in a scrambled but intact form. Think of it like burning a book. The words seem lost in the flames, but if you could track every rising ash particle, every ripple of heat, the information still exists, just in a form we can't easily read. The holographic principle suggests black holes might work the same way, encoding data in the ripples and folds of spacetime itself. Then there's the firewall hypothesis, a concept so violent it sounds like science fiction. Imagine approaching a black hole's horizon, expecting to drift smoothly into oblivion, only to hit a wall of searing radiation, a literal firewall born from quantum chaos. This idea emerged as a desperate fix for the information paradox. If information can't linger at the horizon without breaking quantum rules, maybe it's incinerated on contact, resolving the contradiction in a blaze of energy. Critics argue this violates Einstein's equivalence principle, the rule that free falling into a black hole should feel like floating in empty space, but proponents counter that quantum effects might trump relativity at the edge of a singularity. The stakes here are cosmic. If information survives a black hole's grip, it implies a universe where data is immortal, cycling through cosmic deaths and rebirths like lines of code in an eternal program. Some theories even suggest that black holes could be creators, not just destroyers, their interiors birthing new universes where the ingested information reemerges as fundamental laws. Picture a library where books tossed into a furnace reappear as the building blocks of a new library, their words rewritten into the very bricks and mortar. Yet the most profound implication isn't about black holes at all, it's about dimensionality. If holography is correct, then the information we perceive in 3 dimensions might be shadows cast by a deeper, leaner reality. Black holes could be the universe's way of forcing us to confront this truth, cosmic riddles designed to peel back the illusion of solidity. Every photon swallowed, every atom shredded, might be a clue pointing toward a grander architecture where space-time is a canvas and information the paint. As experiments like gravitational wave detectors and quantum simulators probe these ideas, we're left with a tantalizing thought. The answers might not lie in the void of a black hole, but in the fabric of existence itself. Whether through holograms, firewalls, or some yet undreamed solution, the paradox reminds us that reality's deepest secrets are often hidden in plain sight, written in the invisible ink of quantum code, waiting to be deciphered. The universe seems suspiciously hospitable. The precise strength of gravity, the exact mass of an electron, even the delicate balance between cosmic expansion and contraction tweak any of these values slightly, and life as we know it becomes impossible. Stars wouldn't fuse heavy elements, galaxies wouldn't form, chemistry itself would collapse. This eerie fine-tuning has haunted scientists for decades, sparking a radical question. Is our universe's life-friendly design a cosmic fluke, or the inevitable outcome of deeper laws? Enter the Anthropic Principle, a concept as provocative as it is polarizing. At its core, it suggests that the universe must have properties that allow observers, like us, to exist because otherwise no one would be around to notice. Think of it like a fish pondering why water is so perfectly suited to gills. The water isn't designed for the fish evolved to thrive in the water. Similarly, our universe's constants might not be fine-tuned for life. We're just the unlikely life forms who emerged in the rare corners where conditions aligned. But this raises a deeper puzzle. If the odds of a life-permitting universe are astronomically low, how did we get so lucky? One compelling answer lies in the multiverse. Picture an infinite cosmic lottery where countless universes bubble into existence, each with its own random set of physical laws. Most are stillborn, collapsing instantly or stretching into barren voids. But in a tiny fraction, the numbers align perfectly and life gets a chance. We're not lucky, we're inevitable because we can only exist in the universes where the math works out. String theory's landscape of possible vacua, with its 10 to the 500 potential configurations, offers a staggering playground for this idea. Cyclic cosmology offers another twist. If the universe undergoes endless cycles of expansion and contraction, each iteration might tweak the constant slightly, like a cosmic dial searching for the right frequency. Over countless cycles, a universe like ours eventually emerges, not by chance but by persistent trial and error. The philosopher Charles Sanders Peirce once speculated that nature habits, that laws themselves evolve. In a cyclical cosmos, those habits could refine themselves across eons, converging on conditions ripe for complexity. Yet critics argue these explanations merely kick the can down the road. A multiverse still needs rules governing how universes vary, a meta-law that itself demands fine-tuning, and cyclical models struggle to explain why entropy resets so neatly with each cycle. Some physicists, like Lee Smolin, propose a form of cosmological natural selection. Universes that produce black holes might reproduce, with slight mutations in their offspring's laws. Over time, black hole-rich universes which coincidentally favor life-friendly constants would dominate. It's Darwinism scaled to the cosmos, with black holes as the evolutionary engine. The wildest implication: if dimensionality itself is variable, if some universes have more spatial dimensions or different quantum rules, then the Anthropic Principle might explain why we experience exactly 3 dimensions of space. More dimensions would destabilize planetary orbits, fewer would limit complexity. Our universe's structure could be the Goldilocks zone for observers, a cosmic sweet spot where physics and geometry conspire to allow minds to emerge. Whether you find these ideas exhilarating or unsettling, they force a humbling perspective. The constants we measure might not be fundamental laws, but local bylaws, contingent features of a universe that's one possibility among infinite others. And that's the real power of the Anthropic Principle, not just to explain fine-tuning, but to redefine our place in the cosmos. We're not the center of existence, but witnesses to a rare alignment, a fleeting moment where the universe woke up to ponder itself. Quantum gravity is where the greatest mystery in modern physics lurks, a chasm between two towering theories that refuse to harmonize. On one side, quantum mechanics rules the subatomic world with probabilistic waves and particles that exist in multiple states until observed. On the other, general relativity paints spacetime as a smooth, bending fabric, warped by massive objects like stars and black holes. Both frameworks are astonishingly accurate in their domains, yet when they collide, like at the heart of a singularity or the instant of the Big Bang, the math explodes into nonsense. It's as if the universe operates with two incompatible instruction manuals, each flawless on its own, but together they're gibberish. This isn't just an academic puzzle. The rift between these theories means we fundamentally don't understand reality's bedrock. Take the birth of the universe. General relativity suggests a singularity, a point of infinite density where all known laws break down. But infinities in physics are nature's way of saying, I don't work like this. Quantum mechanics, meanwhile, thrives on granularity, suggesting that even spacetime itself might be woven from discrete, indivisible threads. Reconciling these visions isn't about tidying up equations. It's about rewriting the story of existence from its first sentence. Enter loop quantum gravity, one of the boldest attempts to bridge the divide. Imagine spacetime not as a continuous sheet, but as a shimmering network of interconnected loops, a cosmic spiderweb where each thread carries a tiny, quantized unit of area or volume. In this framework, the smooth geometry we perceive is an illusion, like mistaking a pixelated image for a painting when viewed from afar. The loops vibrate, twist, and interact, creating the dynamic fabric of reality through their dance. Crucially, this approach banishes singularities. Instead of a Big Bang emerging from infinite density, loop quantum gravity proposes a big bounce, where a previous universe collapsed to an ultra-dense state before rebounding into our own. It's a vision where time doesn't begin but transforms, like a phoenix rising from quantum ashes. Causal dynamical triangulation takes a different path, treating spacetime as a mosaic of tiny, triangular building blocks. Picture assembling a curved surface from flat Lego pieces. The smaller the blocks, the smoother the curve appears. In this model, the universe at its tiniest scales is a chaotic froth of these geometric fragments, but as you zoom out, they statistically average into the smooth spacetime we know. What's mesmerizing is how this approach naturally generates an arrow of time. At microscopic scales, the triangles can connect in any direction, but on larger scales, a preferred time dimension emerges, like the grain in wood guiding a carver's chisel. String theory, meanwhile, approaches the problem by adding extra dimensions and vibrating strings as reality's fundamental notes. But these frameworks share a tantalizing hint. Spacetime might not be fundamental at all. It could be an emergent property like temperature arising from the jostling of atoms. If true, then the conflict between quantum mechanics and gravity might be a mirage, a sign we're describing shadows cast by a deeper, hidden structure. The stakes couldn't be higher. Unifying these theories wouldn't just fill a gap in our knowledge. It could reveal how dimensions crystallized from chaos, why the universe favors matter over antimatter, even whether time travel is mathematically possible. Experiments are already probing these ideas, from gravitational wave detectors hunting for quantum ripples in spacetime to tabletop experiments simulating black hole conditions. Each result, whether confirmation or contradiction, nudges us closer to a theory of everything, a single narrative that stretches from the quantum foam to the cosmic web. What's thrilling isn't just the potential answers, but the questions we haven't yet thought to ask. As physicist Niels Bohr once said, every great and deep difficulty bears in itself its own solution. The chasm between quantum mechanics and gravity isn't just a problem to solve, it's an invitation to reimagine reality itself. David Bohm's vision of reality turns the universe inside out. Imagine a cosmic origami where everything you see, stars, galaxies, even the space between them, is just the unfolded edge of a deeper, hidden structure. This is the implicate order, a radical idea suggesting that what we perceive as separate objects are actually temporary expressions of an underlying unity, like waves rising from the ocean only to dissolve back into it. For Bohm, the apparent solidity of the world was an illusion, a holographic projection from a realm where time, space, and dimensionality operate by rules we can barely fathom. What makes this concept electrifying is how it intersects with the birth of dimensions. If Bohm was right, the phases we've been exploring, the unfurling of spacetime from quantum foam, the crystallization of hidden dimensions, might not be independent events but ripples in a far grander process. Think of it like watching a movie and mistaking each frame for reality, unaware that the true story lies in the unspooling reel. The implicate order suggests that the Big Bang, the emergence of forces, even the arrow of time could be secondary phenomena, surface patterns woven by a deeper, more entangled reality. Bohm's inspiration came from an unlikely place, plasma physics. Observing electrons in a plasma, he noticed they behaved less like individual particles and more like interconnected nodes in a flowing whole. This led him to propose that quantum particles aren't truly separate, they're guided by a pilot wave of hidden information, like dancers responding to music only they can hear. Extend this idea to cosmology, and the birth of dimensions takes on a startling new light. The three spatial dimensions we experience might not be fundamental, but the most stable harmonics in a multidimensional symphony, the notes loud enough for our limited instruments to detect. The holographic principle dovetails eerily with this vision. Just as a hologram encodes a 3D image on a 2D surface, Bohm's implicate order implies that our universe's structure is a projection from a boundary we can't see. Some string theorists argue this boundary could reside in higher dimensional space, with our reality unfolding like a shadow on a cave wall. The phases of dimensional emergence, from the symmetry breaks of the early cosmos to the curling up of extra dimensions, might then be stages in an eternal process of unfolding and enfolding, like breath moving in and out of an infinite lung. Critics argue Bohm's ideas are more philosophy than physics, lacking testable predictions. Yet recent experiments in quantum entanglement, where particles remain mysteriously linked across distances, hint at the kind of non-local connections his theory requires. If information can transcend space and time, perhaps dimensionality itself is more fluid than we thought. Some researchers even speculate that dark energy, that enigmatic force accelerating the universe's expansion, could be a pressure from the implicate order, a hidden dimension slowly leaking into our own. The real magic of Bohm's framework isn't just in rewriting the past, but in reimagining the future. If reality is fundamentally unified, then probing the birth of dimensions isn't just about tracing history. It's about deciphering the syntax of a cosmic language where every law of physics, every constant, is a word in a sentence we're only beginning to read. And that sentence might still be being written. White holes are black holes' cosmic counterparts, not cosmic vacuum cleaners, but cosmic fire hoses, spewing out matter and energy with relentless force. While black holes trap everything that crosses their event horizon, white holes theoretically reverse the process, forbidding anything from entering while ejecting material at impossible speeds. Picture a waterfall running uphill, defying gravity's pull. These bizarre objects have never been observed, but mathematically, they're just as valid as black holes in Einstein's equations of general relativity. Flip a black hole's equations in time, and you get a white hole, a symmetry so elegant it begs the question, could our universe itself be the aftermath of a white hole's eruption? Some cosmologists have taken this idea seriously. If a white hole's explosive output resembles the Big Bang's fiery birth, then our entire cosmos might not be the result of a singularity, but the debris from a higher dimensional white hole's detonation. Think of it like a champagne cork popping. The universe bursts into existence not from nothingness, but from a pressure release in the fabric of reality itself. In this scenario, the white hole isn't just an object in space. It's the origin of space, a dimensional rupture where the laws of physics rewrite themselves. This ties eerily into loop quantum gravity's predictions. When a black hole collapses in this framework, it doesn't crush into a singularity but rebounds in a quantum bounce, a white hole birthing a new universe from the ashes of the old. The matter it ejects wouldn't just be random debris. It could carry imprints of its former structure, like a burned book whose ashes still hold the faintest traces of ink. If true, our universe's constants, the strength of gravity, the mass of electrons, might not be arbitrary, but inherited from a parent cosmos's dying moments. String theory adds another layer of intrigue. If white holes exist, they could be bridges between brains' higher dimensional membranes floating in a bulk space. A white hole in one brain might funnel matter into another, creating a new universe with its own dimensional rules. It's as if reality is a vast game of cosmic pinball, with each white hole launch spawning a fresh playfield with different physics. Yet white holes face a glaring problem: thermodynamics. How could something eject energy indefinitely without violating entropy's relentless climb? One possibility is that white holes are fleeting, their outbursts lasting mere instants before collapsing or stabilizing. Another is that they're not truly isolated but part of a larger system, wormholes linking them to black holes elsewhere, forming an eternal cycle of ingestion and expulsion. The most tantalizing idea: white holes might not be objects at all, but events, singular moments in cosmic history where dimensions reconfigure. The Big Bang, then, wouldn't be a point in space-time but a phase transition, like ice melting into water, where the universe's very geometry changes state. If so, searching for white holes isn't just about finding cosmic oddities. It's about decoding the universe's deepest architecture, one eruption at a time. The Planck epoch is where physics loses its footing, a realm so extreme that even our most advanced theories crumble into uncertainty. Picture a storm raging at temperatures of 10 to the 32 degrees Celsius, where space-time itself churned like a quantum sea. This was the universe's opening act, a fleeting sliver of time so brief it makes a nanosecond seem eternal. Here, gravity wasn't just a force, it was a quantum phenomenon, flickering in and out of existence alongside the other fundamental forces, all fused into a single, indescribable unity. In this primordial chaos, dimensions themselves were fluid, unstable. Some theories suggest that all 10 dimensions predicted by string theory existed symmetrically, vibrating in a soup of pure potential. Then, as the cosmos cooled past that critical threshold, the Planck temperature, the first fractures appeared. Like ice forming on a turbulent lake, space-time began to crystallize. 3 spatial dimensions unfurled into the expanse we recognize today, while the others coiled into knots so tiny they vanished from view. This phase transition wasn't gentle. It might have been a violent symmetry break, a cosmic shattering that sent shockwaves through the newborn universe, imprinting patterns we still see in the cosmic microwave background. Loop quantum gravity offers a different lens. Imagine spacetime not as smooth fabric, but as a mesh of interwoven loops, a quantum network where each thread carries a tiny parcel of area or volume. In the Planck epoch, this network would have been a seething foam with loops constantly forming and dissolving. As the universe expanded, these loops stabilized, locking into the structured lattice we now perceive as dimensions. It's like watching a turbulent river freeze solid, the chaos of rushing water giving way to the rigid geometry of ice. But the wildest idea comes from holographic principles. What if the Planck epoch wasn't a temporal event at all, but a computational one? Some models propose that our three-dimensional reality emerged from a two-dimensional boundary, like a hologram flickering to life. In this view, the crystallization of dimensions wasn't a physical process, but an informational one, a cosmic algorithm booting up, translating code into the space-time we inhabit. The Planck scale, then, would be the universe's resolution limit, the pixel size below which reality blurs into noise. Yet for all their brilliance, these theories share a humbling truth. We're peering into a void where conventional language, even mathematics, struggles to tread. The Planck epoch isn't just a time before atoms or stars. It's a realm before cause and effect, before time had meaning. It's the ultimate frontier, a whisper from the edge of nothingness. And decoding its secrets might not just reveal how our universe began, but how all possible universes could. Empty space is anything but empty. Even in the deepest void between galaxies, where no stars shine and no matter lingers, the fabric of reality hums with an invisible energy, a seething quantum dance of particles flickering in and out of existence so fast they defy measurement. This is vacuum energy, the universe's hidden heartbeat, and it might hold the key to understanding how dimensions themselves emerged from chaos. Picture the quantum vacuum like a stormy ocean. Waves rise and crash unpredictably, their energy churning beneath the surface. In physics terms, these waves are virtual particles, electron-positron pairs, quarks, even entire atoms, that borrow energy from the vacuum to exist for fleeting moments before vanishing back into the void. According to Heisenberg's uncertainty principle, this isn't just allowed, it's inevitable. The cosmos teems with these ephemeral fluctuations, and their collective energy could be the engine behind some of reality's most profound mysteries. One of those mysteries is dark energy, the force accelerating the universe's expansion. If vacuum energy permeates all of space, its repulsive pressure might be pushing galaxies apart faster than gravity can pull them together. But here's the twist: when physicists calculate how much energy the quantum vacuum should contain, the numbers are catastrophically wrong, off by a factor of 10 to the 120. This cosmological constant problem is the largest discrepancy between theory and observation in all of science. Some researchers think the answer lies in the birth of dimensions themselves. During the universe's earliest phases, when dimensionality was still settling into place, vacuum fluctuations might have been trapped like echoes in a canyon. As three spatial dimensions expanded and others curled up, pockets of vacuum energy could have crystallized into the fabric of space-time, their residual tension now driving cosmic acceleration. It's as if the universe never fully relaxed after its violent birth, leaving behind a sort of quantum stiffness that still pushes space apart. But vacuum energy's role might go even deeper. Some models suggest that these fluctuations could act as cosmic seeds, triggering the nucleation of entirely new universes. Imagine a bubble forming in boiling water, except the bubble is a fledgling cosmos, and the water is the quantum foam of a higher dimensional multiverse. In this scenario, vacuum fluctuations in a parent universe might reach critical energy densities, warping spacetime so severely that a new universe pinches off, complete with its own dimensional structure and physical laws. Our own Big Bang could have been one such event, a quantum burp in an infinite sea of nothingness. String theory adds another layer to this puzzle. In certain brain world scenarios, vacuum energy isn't just a passive backdrop but an active sculptor of higher dimensional geometry. Collisions between brains, those theoretical membranes floating in a bulk space, could release vacuum energy like a cosmic spring uncoiling, fueling the explosive expansion we call inflation. The wrinkles and folds left behind in this process might have dictated how many dimensions stabilized into our observable reality, while others remained hidden. Yet for all its theoretical promise, vacuum energy remains maddeningly elusive. Labs have detected its effects indirectly, like the Casimir force, where two metal plates placed micrometers apart in a vacuum feel a slight push from the quantum froth outside them. But directly measuring its influence on cosmic scales or proving its role in birthing universes is a challenge that could redefine physics. Future experiments, like ultra-precise measurements of the cosmic microwave background or tabletop quantum gravity simulations, might finally reveal whether vacuum energy is the silent architect of dimensional reality or just one piece of a far grander puzzle. What's certain is that the quantum vacuum isn't a static stage for the universe's drama. It's an active participant, a roiling sea of potential that might have set the rules for how space, time, and even existence itself unfolded. And that makes it more than just a scientific curiosity. It's a whisper from the void, hinting at how something as fragile as a fluctuation could shape everything we know. Imagine a mirror hanging at the dawn of time, not reflecting light, but reflecting reality itself. The Biverse Theory proposes exactly that. Our universe might have a twin, born from the same cosmic seed but evolving in perfect opposition, with time flowing backward from its perspective. This isn't just a poetic symmetry, it's a radical reimagining of how dimensionality could have crystallized from the chaos of creation. Picture the Big Bang not as a single explosion, but as a cosmic fork in the road. At the moment of inception, spacetime itself might have split into two branches, one stretching forward into what we experience as time, the other receding into what we'd perceive as the past. These twin universes would share a common origin but diverge in their fundamental arrow of time, like two dancers spinning away from each other in perfect synchrony. In this framework, the birth of dimensions wasn't a solitary event but a coordinated unfurling, with each universe's spatial structure mirroring the others in reverse. The implications for dimensional origins are staggering. If our three spatial dimensions expanded outward from the Big Bang, the mirror universe's dimensions might have expanded inward, curling around their own timeline like a Möbius strip. Matter in our universe would coalesce into galaxies. In the mirror universe, it might dissolve into a diffuse haze, its structure dictated by entropy running backward. Even the forces governing physics could flip: electromagnetism repelling where it attracts, gravity pushing where it pulls. It's as if the cosmos performed a perfect coin toss at inception, and we're living on one side while the other spins unseen. Why would such a duality exist? Some theorists argue it resolves one of time's greatest paradoxes, the low entropy state at the Big Bang. If our universe's pristine order was balanced by its twin's chaos, the combined system could satisfy thermodynamics globally while allowing local violations. Think of it like a ledger. Our universe's improbable fine-tuning is offset by the mirror universe's disorder, keeping the books balanced. Others suggest the biverse emerges naturally from quantum gravity models where time's arrow isn't fundamental but emergent, a fleeting bias in an otherwise timeless multiverse. The most tantalizing clue might lie in the cosmic microwave background. Some anomalies in its temperature patterns, unexplained cold spots, or unusual alignments could theoretically be echoes of our mirror twins' gravitational influence. If the two universes briefly interacted during their early expansion, like soap bubbles touching before separating, the imprint of that contact might linger in the faintest wrinkles of spacetime. Detecting such signatures would require telescopes of unprecedented sensitivity, but the hunt is already underway. Critics dismiss the biverse as untestable metaphysics, a clever idea with no way to falsify it. Yet supporters counter that its elegance lies in unification. Just as antimatter was predicted mathematically before being discovered, the mirror universe could be a necessary counterpart to our own, a shadow woven into the equations of quantum cosmology. Whether it exists or not, the biverse challenges our deepest assumptions that time flows in one direction, that dimensions unfold uniquely, that our universe is alone in the grandest sense. And that's the theory's real power, not just to propose a twin, but to remind us that reality might be far stranger, far more interconnected than our solitary perspective can grasp. If true, every moment we experience, every star born, every particle colliding, could have a counterpart rippling backward in a mirror we'll never see, a silent partner in the dance of dimensions. Consciousness feels inseparable from time, the steady stream of thoughts, the weight of memory, the anticipation of what's next. But if time itself is an emergent property, a latecomer to the cosmic stage, how did subjective experience arise to perceive it? This isn't just a puzzle for physicists, it's a riddle that threads through philosophy, neuroscience, and the very nature of reality. To grasp it, we need to untangle two seemingly contradictory truths: that time might be an illusion woven by the brain, and yet the brain itself is a product of a universe where time wasn't always there. Start with a simple experiment. Close your eyes and try to experience a single, timeless moment. You'll quickly find it's impossible. Your mind automatically strings sensations into a sequence, stitching the present to the just-finished past. Neuroscientists call this the specious present, a window of about 3 seconds where the brain integrates sensory input into a coherent narrative. This illusion of flow is so convincing that we rarely question it. But what if this perception isn't just a quirk of biology, but a reflection of deeper, structural truths about the universe? Some theories suggest consciousness might be a kind of dimensional resonance, a harmonic vibration tuned to the particular way spacetime crystallized in our corner of reality. Philosophers have long wrestled with this. Immanuel Kant argued that time isn't an external property, but a framework the mind imposes to make sense of sensory chaos. Modern thinkers like Julian Barber take this further, proposing that what we call time is just a mosaic of static nows, with consciousness hopping between them like a stone skipping across a pond. In this view, the feeling of duration is a trick of the brain, a way to navigate a reality where all moments exist simultaneously. It's as if the universe is a vast, frozen landscape, and consciousness is a flashlight moving across it, creating the illusion of motion where none exists. But how could such a flashlight ignite in the first place? Enter the physics of emergence. Just as temperature arises from the collective motion of particles, something impossible to predict by studying a single atom, consciousness might emerge from the dance of neurons in a way that mirrors the universe's own dimensional unfolding. The brain's 3-pound web of connections operates at scales where quantum effects and classical biology blur, leading some researchers to speculate that consciousness could be a phenomenon straddling multiple layers of reality. If dimensions themselves emerged from a pre-temporal void, perhaps awareness did too, not as a product of time, but as a parallel development, like two vines growing from the same hidden root. The implications spiral outward. If consciousness is tied to dimensionality, could other universes with different dimensional structures host entirely alien forms of awareness? In a cosmos with 4 spatial dimensions, might sentients perceive reality as a shifting labyrinth of hyper-shapes? And what of timeless realms? Could there be modes of existence so foreign they lack sequence entirely, like a symphony heard all at once? These questions aren't just speculative, they challenge the anthropocentric assumption that consciousness must resemble our own. Yet the hardest problem remains: why does any of this feel like anything at all? Even if we map the brain's wiring or decode the universe's birth, the hard problem of qualia, the raw experience of being, resists purely physical explanations. Some theorists turn to panpsychism, the idea that consciousness is a fundamental property of matter, like mass or charge. In this framework, the emergence of time and the awakening of awareness might be twin expressions of a deeper unity, 2 facets of a single cosmic process. What's clear is that consciousness and time are entwined in ways we've barely begun to fathom. Whether awareness is a fluke of biology, a dimensional echo, or something stranger still, its existence forces us to confront the most profound mystery of all: how a universe of impersonal forces gave rise to something that can wonder about itself. And that's the real magic, not just that we perceive time, but that we perceive it all. The universe's final act hangs between 2 extremes, one a whisper, the other a roar. On one path lies heat-death, a fate so quiet it verges on poetic. Galaxies drifting apart like scattered embers, stars burning out one by one, until all that remains is a vast, featureless void where even black holes have evaporated into faint Hawking radiation. Time in this scenario becomes meaningless, a clock ticking in an empty room. The other path, the Big Crunch, is a cosmic crescendo, gravity finally overcoming dark energy's push, pulling everything back into a fiery collapse that might birth a new universe from the ashes. These aren't just alternate endings, they're reflections of the deepest rhythms in reality's architecture, echoing how dimensions themselves first burst into being. Heat-death is the triumph of entropy, the ultimate victory of disorder over structure. Picture a deck of cards shuffled endlessly until every possible configuration has been exhausted. No more royal flushes, no more patterns, just randomness stretching into eternity. In this cold, dark future, the very dimensions we inhabit could unravel. Some theories suggest that as the universe expands, the fabric of space-time might thin to the point where the forces holding atoms together weaken, dissolving matter itself into a sea of unbound particles. It's as if the universe, having unfolded from a hidden dimensionality, slowly folds back into obscurity, not with a bang but with a sigh. The Big Crunch, by contrast, is a story of rebirth. If dark energy weakens or reverses, gravity could rewrite the cosmos's fate, drawing galaxies back together in a mirror image of the Big Bang. As everything converges, temperatures and densities soar, potentially triggering a new inflationary epoch, a reset button for reality. Here's where dimensionality takes center stage. Just as the birth of our universe might have involved dimensions unfurling from a higher dimensional chaos, a Big Crunch could see them collapse and re-emerge in a new configuration. Imagine a cosmic accordion compressing and expanding, each cycle producing a universe with slightly different physical laws, or even a different number of dimensions. String theory hints at this possibility, with colliding branes or quantum bounces offering mechanisms for cyclical regeneration. Yet these scenarios aren't just about endings, they're about legacy. A heat-death universe leaves no trace, its history erased by time's infinite march. but a big crunch might carry echoes of its predecessors. If information isn't truly destroyed, as quantum mechanics suggests, then each cycle could inherit faint imprints from the last, like a palimpsest scribbled over by cosmic hands. Some models even propose that the constants of physics, the strength of gravity, the mass of electrons, might shift slightly with each iteration, meaning our universe's fine-tuning could be the result of countless cycles honing the conditions for complexity. The choice between these fates hinges on mysteries we've yet to solve: the true nature of dark energy, the stability of space-time, even the possibility of higher dimensions lurking beyond our perception. Current observations lean toward heat death. The universe's expansion seems to be accelerating, not slowing. But science has surprised us before. If dark energy evolves over time, or if our understanding of gravity is incomplete, the story could change. What's certain is that these visions of the end aren't just speculation. They're windows into the universe's deepest rhythms, reminding us that the way things begin shapes how they must end, and perhaps begin again. Gravitational wave astronomy has cracked open a window to the universe's most violent events, colliding black holes, merging neutron stars, but its next act could be even more revolutionary. Imagine these ripples in space-time as cosmic echoes, carrying whispers from epochs before the Big Bang. Future detectors like the Laser Interferometer Space Antenna LISA, slated for launch in the 2030s, will listen for ultra-low frequency waves that might bear scars from cosmic inflation or even brain collisions in higher dimensional space. These waves could encode patterns from the universe's birth phase, like fingerprints left on a frosted window. The challenge: distinguishing primordial signals from the cacophony of black hole mergers and neutron star crashes. It's like trying to hear a single note from a symphony played at the dawn of time, buried under centuries of cosmic noise. Meanwhile, quantum simulators are recreating the conditions of the early universe on tabletops. By cooling atoms to near absolute zero and trapping them in laser grids, physicists create quantum soups where particles behave like they're in a newborn cosmos. These experiments can't replicate the energy levels of the Big Bang, but they're uncannily good at modeling how space-time might emerge from quantum chaos. In 2021, a team at Harvard used a holographic quantum simulator to observe entanglement dynamics that mirrored predictions from string theory, a tantalizing hint that lab-scale physics might illuminate cosmic-scale mysteries. The catch: these simulations are approximations, like sketching a cathedral with a handful of Lego bricks. Yet even crude models can reveal truths about the blueprint of reality. Then there's the hunt for primordial black holes, those hypothetical relics that might have formed from density fluctuations in the universe's first second. Some theories suggest these objects could be microscopic, even atom-sized, carrying clues about the quantum foam that birthed them. Projects like the Subaru telescope's Hyper-Subprime CAM survey scan for gravitational lensing events that betray their presence. If found, their mass distribution could reveal whether they're products of standard inflation or something wilder, like colliding brains or a cyclic universe's collapse. Think of them as cosmic time capsules, their very existence a ledger of conditions we can't observe directly. Cosmic microwave background CMB experiments push even further. The next generation of telescopes, like the Simons Observatory, will map the CMB's polarization with pixel-scale precision, searching for twisted patterns called B modes. These spirals could be the smoking gun of cosmic inflation, or better yet, anomalies that point to pre-Big Bang physics. Some models predict concentric rings in the CMB from black hole collisions in a prior eon, as Roger Penrose's conformal cyclic cosmology suggests. Others look for statistical oddities, regions where temperature fluctuations defy standard predictions. That might hint at a universe recycling itself through endless expansions and contractions. But the boldest experiments aim to test the nature of dimensionality itself. In Geneva, the Large Hadron Collider could one day probe extra dimensions by hunting for missing energy particles that seem to vanish into hidden spatial folds. Tabletop experiments with nanoscale cantilevers search for deviations from Newton's gravity at microscopic distances, where extra dimensions might subtly weaken gravitational pull. And quantum entanglement tests keep pushing the limits of non-locality, probing whether space-time is truly fundamental or just an emergent illusion from deeper, dimensionless connections. The limits are stark, though. Many of these ideas hover at the edge of testability, relying on technologies not yet invented or precision beyond current reach. Some theories, like string theory's landscape of possible universes, might forever remain untestable by their very nature. Yet even null results teach us something, ruling out paths, narrowing possibilities, forcing us to refine our questions. After all, the universe owes us no answers, only mysteries, and that's what makes this hunt so exhilarating. Every failed experiment is a signpost, every faint signal a thread in a story we're only beginning to unravel. From timeless voids to colliding brains, our journey through the multiphase birth of dimensional space reveals a cosmos far stranger than fiction. While mysteries remain, each theory we've explored, whether holographic, cyclic, or quantum, brings us closer to understanding reality's deepest layers. The next time you gaze at the stars, remember, you're not just looking into space, but into the echoes of time's origin. Keep questioning, keep exploring, and let us know in the comments which theory resonates with you. Don't forget to subscribe for more deep dives into the universe's greatest enigmas. What's astonishing isn't just the scale of these ideas, but how they transform our place in the narrative. We're no longer passive observers of a static universe. We're active participants in a story still being written, one where the fabric of reality itself is fluid, evolving, and alive with possibility. Whether it's the holographic principle suggesting we're projections from a distant boundary, or cyclic cosmologies painting our universe as one page in an infinite book, these theories don't just answer questions, they redefine what it means to ask them. Think of it like standing at the edge of an uncharted ocean. Every breakthrough, every failed experiment is another step into the unknown. The tools we've built, from quantum mathematics to gravitational wave detectors, are more than instruments. They're extensions of human curiosity, reaching beyond the limits of our senses to touch the unimaginable. And that's the real gift of this exploration. Not just the answers we've found, but the humility to embrace how much we've yet to discover. So as we wrap up this cosmic journey, here's the most thrilling thought of all. The next great revelation might not come from a telescope or a collider, but from someone like you, watching this video, staring at the night sky and wondering, what if? The universe's greatest mysteries aren't locked away in some distant galaxy. They're hidden in plain sight, waiting for the right mind to piece them together. Until then, keep looking up, stay curious, and remember, the most profound truths often begin as the wildest dreams.